Welcome to section 10.4, where we're going to be talking about convolution with our Laplace transforms and integrals and derivatives. So we're going to get a little convoluted today. But before we get started, I want to introduce two things. First off is function notation. Okay. So if we write f of x equals x squared minus 3, okay, so that tells us whatever we put in, we're going to multiply it by itself and then subtract 3. So if I put in f of 2, I would get 2 squared minus 3, which evaluates out to 1. If I put in f of t, I would get t squared minus 3. Okay. And if I even put in something like f of happy face, I would get happy face squared minus 3. Okay, so whatever I put in place of the argument, the input here, it tells me what to do right here. So even like in calculus 1, we talked about f of x plus h, right? When we were doing our difference quotients, that would be x plus h quantity squared minus 3. So whatever we give it, it squares it and then subtracts 3. Okay. And you'll notice that when I did f of x, I get x squared minus 3, and f of t is t squared minus 3. We can call the variable x or t, or heck, we could even call the variable happy face. It's still just a variable. Sometimes we refer to that fact that we can give the variable any name we want. We call him a dummy variable. Okay. So the second thing that I wanted to talk about is integrals. So if we have the integral of x plus sine of x dx, integrals are nice and they're linear, so they will break apart across addition. But something to note is if I do the integral of x times sine of x dx, this is not equal to the integral of x dx times the integral of sine of x dx. That is not true. So they're linear, so they will respect constant multiples and addition and subtraction, but integrals do not split up over multiplies. And that's actually a main thing that we're going to talk about today, is how we can kind of sort of work around that with convolution and our differential equations in the Laplace transform. All right, so with that under our belt, we're now going to introduce the convolution and some of its related theorems and how we can use this to find Laplace transforms and inverse Laplace transforms. Okay, so this is the tool we'll be talking about. So if we have f of t convolute g of t, this is an asterisk, and sometimes we use asterisks to mean multiply, and we're going to play off of that notation here. But if I were normally just to write this, I would write f of t times g of t, and I just use a simple dot, okay? Or I might even just leave the dot out with it understood being multiplied. But if we use this special asterisk, this star here, when we're playing with functions, that has a special meaning of convolution, which we're about to learn, okay? And I need you to know him forward and backwards. So f of t convolute g of t is defined to be an integral from 0 to t of f of tau times g of t minus tau d tau, okay? And my t's and my taus, when I write them, they look so much alike, probably because tau is the precursor to our letter t. But just like we talked about a couple minutes ago, you can use what we call a dummy variable. So we could call this the integral from 0 to t of f of x times g of t minus x dx. So in place of tau, instead of naming the variable tau, I'm going to name the variable x, so it's easier to distinguish from the t's that I'm going to be using here. Now, you can check this. using a u substitution, but if you do f of t convolute g of t, using this u substitution, you will show that it's equal to g of t convolute f of t. So it is commutative in that nice fashion. And here's how and why we like to use this. Because if we do the Laplace transform of f of t convolute g of t, it is equal to the Laplace transform of f of t times the Laplace transform of g of t, or in other words, capital F of s times capital G of s. Okay, so it's kind of a nifty little thing that we can show that, yeah, our Laplace transform can actually be multiplicative, but you have to go through the convolution. Okay, and if we were to take this equation right here and apply the inverse Laplace transform to both sides, the inverse Laplace transform would undo the Laplace transform, and we'd find out that the inverse Laplace transform of capital F of s times capital G of s is equal to f of t convolute g of t. So let's see this guy in action. Let's do a problem. So let's let h of t be f of t convolute g of t, where f of t is sine of t and g of t is simply a t. Now, notice that when we do the convolution, the first one has a simple input and the second one has a slightly harder input. So whenever, and because the convolution is commutative, whenever possible, I try to make the easier function be the second one so that this is easier to handle. So if we take a look at this guy, so if we do f of t convolute g of t, we're going to get the integral from 0 to t of sine of, and I'm going to use x, not tau's, because otherwise I get myself too mixed up, times t minus x dx, which is equal to the integral from 0 to t of t times sine of x minus x times sine of x all dx. Now, x is the variable, t acts like a constant, so we could factor the constant multiple out here, getting t times the integral 0 to t of sine of x dx minus the integral from 0 to t of x sine of x dx. Okay, ooh, got that right at the end here. The first one's easy. The second one, we're going to need to do some integration by parts because, as we saw at the beginning, this is not, the integral doesn't split up over the times. So we'll get equals, let's do the integration by parts piece first. So let's let u equal x and dv equal sine of x dx. Then du is equal to dx, and v would be equal to negative cosine of x. So this second piece is going to be, using integration by parts, minus, because of this guy, minus the integral of, the integral of u dv is equal to uv. So we'll have x times negative cosine of x, evaluated from our limits of 0 to t, minus the integral of v du, which is the integral from 0 to t of cosine of x dx, which is easier to handle. And then let's not forget our first guy right here, which was t times the integral of sine of x dx, but we can, well, yeah, I'll just do that right now. So t times the integral from 0 to t of sine of x dx, okay? And remember, this minus sign right here is going to distribute over all of the integration by parts. And we're at about 10 minutes, so let me stop here and we'll pick up there at the beginning of the next video.